guys, welcome back to another circular motion physics problem. Tension in a vertical circle. Okay, so a bucket of mass 2.05 kilograms is whirled in a vertical circle of radius 1.15 meters. At the lowest point of its motion, the tension in the rope supporting the bucket is 26.0 newtons. A, find the speed of the bucket, and B, how fast must the bucket be moving at the top of the circle so that the rope does not go slack. So this video number 78 is actually quite similar to what we did in video 76. We were also using a vertical circle and a ball being whirled in a vertical circle. Here it's a bucket. Same idea. It's just a mass at the end of the string. The difference was, in video number 76, we were given the speed and we had to find the tension. In this question, we were given the tension, we have to find the speed at various points. So as is with any physics problem, I want to start off by drawing a picture. Okay, so here we go. We've got a vertical circle, so just trace out a circle. Now, whenever you hear vertical circle, you immediately must think that gravity is going to play a big effect here. If you have a horizontal circle, gravity's not playing the same kind of effect. Okay, so the radius of my circle is r equals 1.15 meters. Now, I've got a bucket being spun in the circle, right? So for part A, we're told that the tension is 26 newtons at the lowest point of its motion. Okay, so I'm going to draw this bucket at the lowest point in its motion. And apparently the tension at that point is 26 newtons. Now, because it's attached to a string, the tension is going up. So Ft equals 26.0 newtons. Now, as a direct result of this, I'm going to let up be the positive direction. We're only going to deal with vertical forces here. So I'm going to just let up be positive. So the other force we're dealing with in this problem is gravity. And gravity is, of course, going straight down towards the center of the earth. So there's that. Now, in order to help us calculate gravity, we're given the mass of the bucket, which is 2.05 kilograms. So let's get started. For part A, find the speed of the bucket. Obviously, at this point, here's the thing. With centripetal motion, the speed of the bucket is going to be the same at any point along the circle. But because we have the tension at the lowest point in its motion, it makes sense for us to use that point to find the speed. Okay, now speed is a kinematics quantity. Now we're going to use dynamics, in other words, Newton's second law, in order to find acceleration, which will then help us find the speed. Okay, so F net equals ma. Always start off with Newton's second law. Now, in this question, we're dealing with circular motion. So the net force is a centripetal one, which is equal to mass times a centripetal acceleration. Now, my forces in the circular direction, in the radial direction, in the positive, I have Ft, in the negative, I have Fg. So Fc is going to be Ft minus Fg equals m. Now, centripetal acceleration. Okay, so we saw in earlier videos that centripetal acceleration is equal to v squared over r. Okay, the tangential speed divided by the radius of the circular motion. So mv squared over r. At a certain point, you're simply going to end up memorizing that Fc equals mv squared over r, and that's fine. Just make sure you know where it comes from. Okay, so we're trying to isolate v here, and v is being squared, so let's get v squared by itself. So in order to do that, v squared right now is being multiplied by mass and divided by radius. So to get it by itself, we have to multiply by radius and divide by mass. Okay, so if I do this to both sides, I'll get v squared by itself. So then v squared is equal to, because the r's cancel, the m's cancel, r over m ft minus fg. Okay, so let's start plugging in our numbers and seeing what we get. So the radius of the circular motion is 1.15 meters. The mass of the bucket is 2.05 kilograms. Force of tension, 26.0 newtons. Minus force of gravity, well, you know Fg is simply equal to mg. So we multiply the mass, 2.05 kilograms, times the acceleration due to gravity, 9.8 newtons per kilogram. Okay, so that allows us to cancel out the units of kilogram. Okay, now next line, let's grab another sheet here. We're simply going to plug this into our calculator and find out what we get here as a result. Okay, so we're still dealing with v squared. So v squared is equal to this expression. Okay, when you solve this, you're going to get 3.3154 meters squared per second squared. So in order to get v by itself, you have to take the square root of both sides. Okay, so square root both sides, and you end up getting v is equal to 1.82 meters per second. Okay, so there's your answer for part A. So at any point in the circular motion, you have this speed. And just as a check, we are correct to the right number of sig figs because we have 3 spots. Same with the question. The least certain value has 3 significant figures. So we're good at that respect. Okay, so now we're going to try part B. Remember, part B says, how fast must the bucket move at the top of the circle so that the rope does not go slack? Okay, so now while there are a lot of things in this question that are constant at any point in the circle, such as the speed, the mass, the force of gravity, the radius of the circle, there are some things that change as the bucket makes its way around. That is the force of tension. Tension is the greatest at the bottom of the circle. Okay, just imagine if you were whirling that bucket around, you have to use the most muscle in your arm when the bucket's at the bottom. When the bucket's at the top, you feel like it's almost nothing going around. Okay, so that's the idea. Just when the tension becomes 0 at the top of the circle, that's when the rope does not go slack. At that point, just when the tension becomes 0. Okay, so here we go. We're going to go to part B. Okay, how fast does it have to move at the top of the circle? So let's just do a really simple diagram here. I mean, I'm just going to draw the top half of the circle, and you've got your bucket, which is going to be upside down at that point. So there's my lovely artistic bucket. And at this point, we've got force of tension that's going to be going down, right? Because that's the direction the string is facing. And we've also got force of gravity going down as well. Force of gravity is always going down. Okay, now because both of my forces are going down in this part, I'm going to let positive be down. Okay, here we go. So here we're dealing with the top, and I'm just going to go ahead and jump into Newton's second law once again. F net equals ma. And of course, we're dealing with the centripetal forces here. Okay, so F net in the centripetal direction or in the radial direction, we've got both of them going in the same direction, in the positive direction. So it's going to be Ft plus Fg equals m. And then, of course, a centripetal is v squared over r. And same as before, we're looking for v squared. If you notice, the only difference is in part A, we were subtracting Ft minus Fg, right? Because they were going in opposite directions. Here, we're taking the sum because they're going in the same direction. Okay, so we need to get v squared by itself. Same procedure as before. To get m and r out of the way, we're going to multiply by r over m, because that cancels the r, cancels the n. So you end up with v squared equals r over m Ft plus Fg. Now, like I mentioned, at the top of that circle, your tension force goes to 0. At that instant that the tension force becomes 0, that's the point where the rope just does not go slack. Okay, and that's what we're going to be using to find our speed. Okay, so if that's 0, we end up with v squared equals r over m times Fg. Fg is also known as mg, right? So then what happens? Your masses cancel. So you get v squared equals rg, or v equals the square root of rg. Now don't go ahead and memorize that formula for a circular motion bucket in a vertical circle, because every question is a little bit different. And you want to make sure you customize your answer for that particular problem. Okay, so we're going to get r, which is 1.15 meters. G is 9.8 meters per second squared. Take the square root of that. So you end up getting v is equal to 3.36 meters per second. Okay, now here's the thing. This is the speed when tension just becomes 0, right? If the tension is 0, technically the rope is slack. So, because this is the speed when the rope just goes slack, for it not to go slack, your speed has to be greater than 3.36 meters per second. Okay, and that's your final answer. So if your speed is 3.361, it's not going to go slack because it's greater. So there is your answer for part B. V is greater than 3.36 meters per second. Okay, so that's it for this video, guys. I hope you enjoyed it. If you did, be sure to click that like button and subscribe to Physics in the Flesh so you never miss a video from me. Thank you so much for watching.